This video is one of the videos in the sequence on integration applications, and this video covers the density example. So what we want to imagine in terms of density is that density is how closely packed a material is. If you've had any study in physics, you've probably heard of density a lot. It depends mostly on some sort of material's intrinsic properties, and the full concepts of where density comes from is best left to your physics and chemistry classes. So we're just going to focus on finding mass, considering we are already given a density function. So we're not focusing on deriving density functions or understanding the concept, just the math behind how to find mass if you are given length and density. So the most simple formula that's going to govern our approach here is just the basic identity, assuming that you had uniform density, mass, and length. The formula that we're looking at is that density, which is used usually denoted with a Greek letter rho, is equal to mass divided by length. So solving that letter for mass would then be equal to density times length of the object. So we're going to begin with the understanding and assumption, just to make the math as simple as possible, that we are going to look at density of one-dimensional objects. So even though we had to illustrate this rod here in our first example as something that has two dimensions, imagine that it's infinitely thin, that it is a one-dimensional rod. We'll see how we can work on some two-dimensional examples later in this video, but in order to look at full three-dimensional materials, you'll need multivariable calculus, and you'll have to stay tuned for that. Okay, so let's begin with this one-dimensional example. Let's say that our rod stretches from length A to length B, and obviously we're going to assume that we don't have uniform density. If we did have uniform density, we could just use this simple formula and compute the mass with no issue. But if density varies on this rod, so let's say the density at A is different than the density of B, then we can't use that simple identity. But we're going to try to reduce the problem to use that identity as much as possible. So we'll go ahead and assume that the rho of x function is the density of the rod at x, and how we're going to handle the fact of finding the mass when the density varies is we're going to break the rod up into little intervals. Just like we've done in all of our applications up until this point, we're going to form a partition of that interval a to b. So here we are looking at the ith interval, x sub I minus 1 up to x sub I. And we're going to have the assumption that on this interval, density is constant, because as we know what's going to happen when we approximate the density, we'll use a Riemann sum, and then as we break our interval up into more and more pieces, the delta x is going to go to 0, and we'll get the exact mass formula. So let's look at the mass on this ith interval. Okay, on the mass on the ith interval is going to be the product of the density of, and we'll just use we'll consider it like the average density value. Times the length, delta x, which is equal to x sub I minus x sub I minus 1. And that's going to be uniform on all intervals, because that's what a partition is. Okay, so that's the mass on the ith interval. And if we wanted to find an approximate for the rod, we would add up those masses. We'd range our I from 0 to n minus 1, and n is the number of partition points. And then the exact mass we're going to let n go to infinity. As n goes to infinity, the width of each interval is going to go to 0, and we get the interval coming out integral from a to b, the density function dx. So it's a very straightforward integral as the delta x goes to 0. Okay, so let's check out an example where we go ahead and use this identity to our advantage. Let's say a one-dimensional rod is placed on the x-axis with its left end at the origin and its right end at x equals 4. Its density is given by the density function rho of x equals 4 e to the negative x, and we want to find the rod's mass. Okay, so our rod is positioned from 0 to 4. So we're breaking it up into pieces from 0 to 4, and we're integrating the density function on that integral. This is a super easy integral to do. You can pull the 4 out. Okay, when I see this, I don't really need to do a physical u sub, but I'm kind of used to integrating. So if you're unsure how to do this, you could make your u equal to negative x, but I'm just going to use, I guess, power of recognition to recognize that this is going to have antiderivative negative e to the negative x. And we're evaluating from 4 to 0. So 4 times negative e to the negative 4 minus e to the negative 0. So that's going to be 1. Okay, and I almost went on autopilot and marked this the end of the problem, but when you're telling someone a physical quantity, we're looking at mass, this should have units attached to it, so this should be measuring kilograms. In single variable calculus, there's only so much we can do mathematically, so the motivating factor for learning multivariable calculus and continuing your study in mathematics is that you aren't restricted to making all these simplifying assumptions. With some multivariable calculus, which you will hopefully get at some point in the future, you will learn how to extend this concept of finding the density to a more complicated object that is not one-dimensional, but you'll have to stick around until then. So this is the end of our study of density, and in the next video we will go ahead and take a look at the application of integration to work.